So today we're going to be looking at a topic which is of pretty big importance to the whole big picture of this experimentation that we're doing and trying to understand Tesla's conception of electricity and the ether, and that is the electrostatic phenomena. So here on the bench we have our experimental setup replicating what was done in Tesla's first lecture. And we're going to be kind of showing that the luminous effects that are produced in the fluorescent tubes are mostly due to, or mostly or all due to electrostatic field effects and not electromagnetism, as is currently supposed in modern day. When Tesla talks about this, and that's on page 174 of our reference book. So on page 174, he talks about how the electrostatic phenomena has been overlooked by experimenters since the Hertz experiments supposedly proved the existence of electromagnetic waves propagating in the ether. And the Hertz experiments were the first demonstrations of wireless electrical action, and they came at a time where there was no experimental proof of the Maxwellian idea of propagating electromagnetic waves through the ether. So that generated, the results of the Hertz experiments generated quite a lot of excitement in this direction, and Tesla is saying that this excitement sort of made people overlook the electrostatic phenomena, and that really that was actually the largest driving factor in a lot of these experiments. The first thing he points out is that the reason maybe some of this stuff wasn't noticed before is that the apparatuses that were used for these types of experiments did not allow for the production of large electrostatic effects. So the Hertz experiment basically had a power supply here, and that would discharge into a high voltage electrical coil. So this is a really big coil with a lot of turns, and when you impulse a current into it, it's going to produce some pretty high voltages. And on the terminals of this coil, there was attached a small little spark gap and a metallic sphere to add some extra capacitance to the terminals to try to increase the potentials that were used for these experiments. And what Tesla was saying was that this does not actually allow for the production of large electrostatic effects, because what we're doing is we're shorting the terminals of the inductor through this spark gap. And this, when it's firing, has an incredibly low resistance. So we're shorting these two terminals together, and you can't really build large potentials across such a small resistance. And the resistance decreases as these capacitances increase on the terminals. So it's producing large currents, but is not really an ideal setup for producing large potentials. So Tesla's configurations that he's using kind of addresses some of these problems which he's noticed, and this is what allows him to actually see these effects much easier than with the devices like here in the Hertz experiments that don't really allow for large electrostatic effects. So we'll kind of look at some of the experiments that he pointed to, which led him to these conclusions. Okay, so this is a setup, same one we've been running on this channel. We have the outputs here of the high voltage transformer going to these steel spheres. And what we're gonna see is that if I place this fluorescent tube around these spheres, we'll get it to illuminate. However, if I place it right in the middle of these spheres, there's going to be a plane in between these spheres that forms where the potential cancels out. So basically we have the transformer running and putting high voltage, high frequency alternating currents across these two spheres. So during each wave amplitude, these are going to be alternately charged, positive and negative, and then negative and positive. So what we're going to see is that if we go right in the middle, the potentials neutralize each other and cancel out. And we get basically no induction here on the fluorescent tube. Whereas if we just move it slightly one way or the other, we'll get it to light up real brightly. This is a good demonstration of what we're talking about, because if we were getting electromagnetic waves passing from one sphere to the other, we would expect the amplitude. Basically, we're picturing a wave just traveling across these two spheres. So we would picture the energy would be the same here, or possibly just the maximum right in the middle. But that's actually not the case, as we'll see. So I'll turn it on. Put the lights down. Whoops. Not that far down. All right, so we got our potential on the terminal. Now we can see that if we have the tube in the vicinity of this thing, it's going to illuminate. Now if we come stand over here, I'm going to put the tube in between and just slowly scan it through. We can see right about here, it's hard to get it right in the middle, but right about there, the potential seems to die out. Now, if we got we can make it easier to see if we use a smaller tube. So I'm gonna switch to this tube now, which is a fluorescent tube as well, just a smaller diameter. So we're going to try the same thing, and we'll see a more profound effect with this smaller tube. So, okay, going to do the same thing now. Now, it's not due to when you're first viewing this, it may be possible to think that, well, you know, as you bring the tube in this way, you're actually getting further from the sources of alternating potential. So we know that the potential decreases as you get further away from an object. So maybe we could be thinking like, oh, maybe the field intensity just isn't great enough here to actually illuminate the tube. So what I'll do now is I'll show you that if I have the tube around here, I can go a distance greater than, you know, from halfway between these spheres, and we can still keep pretty good illumination on this thing, even though we've traveled further than half the distance between the spheres. So that'll just show it's not that the field is just not strong enough to illuminate it here in the middle, but it's that there's an actual cancellation occurring here due to the alternate sign of the potentials on these spheres. So we'll just do that real quick. Okay, there you go. So you can see right now we're more than halfway between the distance we've moved away is more than halfway between the two spheres, and we're still keeping a good illumination. Whereas if we, stayed in between them, you can actually see the dark spot moving up and down the tube as I move in and out of it. I don't know how well it's coming out in video. So you can see that in the ability to observe this effect depends on, keeping this thing, as much in that middle plane as possible. So even if you have the tube right in the middle, if you're holding it, a little bit like this or a little bit like this, you still won't be able to see it as well. You have to try to hold it perfectly perpendicular to the axis connecting the centers of these two spheres. So you can kind of mess with that a little bit, but you can get it to where you actually have like zero induction in between these two things, and you get no illumination. Another factor that plays into that is the radius of the tube you're using. The larger the radius, the less you're going to be able to fit in that cancellation zone. So you kind of need something, a little smaller to really see it well. But yeah, I basically, if I move from here to here, I get the cancellation. But if I move from here to here, it still stays illuminated. So that's just kind of a good demonstration here, showing what Tesla was talking about. So the reason that we're able to observe some of these more pronounced electrostatic effects on this setup, even though it does look pretty similar to the setup for the Hertz experiment, is I'm not shorting out the terminals of the secondary. So here I have no gap, which is short circuiting here our high voltage transformer. So I allow the voltages to build on each of these output terminals instead of shorting it. So what we can do here to show how a spark between the terminals will decrease your performance greatly as far as illuminating the tube goes, we can just take these balls here and move them in. Just going to move them in to a distance where they're close enough to not allow any potential or any substantial potential to build across them before it breaks. And this is going to limit the degree of the electrostatic effects which we can observe on the outputs because of that limiting the potential. So I've moved them close enough now to where we should be able to start arcing as soon as we break our circuit. So now I have these things set up to where I have restricted the ability of our setup to produce pronounced electrostatic effects because of the small gap in between these two spheres. They're gonna short, and when you get that shorting between the terminals, you're basically putting a very small resistance in between our outputs, and that's going to limit our rising potential. And as we'll see, it'll limit the ability to which we can illuminate these fluorescent tubes. So let's kill the lights and turn it on. And we'll see as soon as I turn it on, it's going to start arcing. So we saw that I was able to get a little bit of illumination out of this, but the effect was very weak. I had to pretty much put it right up against this thing in order to get anything to show. So now I'm going to show you what's going to happen if we just separate these slightly. This is going to slightly increase the resonant frequency of our system, but more importantly, it's going to allow the potentials to build up on these two spheres, and it's not going to break the airspace in between them. So we'll do the same experiment, and you can see what big a difference it makes just to not have that arc playing across the spheres. See, I'm right here, and I've already began to illuminate, and it's already stronger than it was before. So you can see the distance at which you can get illumination is much greater. This will kind of help to show it a little better. And then to make this effect even more pronounced, I've gone ahead and decreased the distance between the spheres even more. So now we're going to be, even though we did have a spark playing between the spheres last time, we still had a reasonable distance between the spheres, which allowed for a buildup of lesser potentials, even though we didn't allow it to reach its maximum potential. We were still getting some voltage on these spheres because the potential has to reach a certain amount or a certain level before that airspace is broken. And now what we've done is we've limited that voltage threshold for breakdown to a very small voltage. So now the electrostatic effects on the terminal are going to be even smaller than before. And we'll see that we won't really be able to get anything out of this. So I'm just going to turn it on. So we can see that we get only very faint illumination when we're directly next to this thing. But the second we take it off, it immediately disappears. Whereas when we had separation between these things, you know, we could get it to illuminate all the way out here.